we have Mahadi Hajedi. He's actually got quite a few affiliations, but I believe this, he can correct us if I'm mistaken here, but I think this work has been done while he's at the University of Michigan. Um, and this work here is quite a really interesting, prominent application scenario where the types of advantages that federated systems have can often shine. In this case here, trying to detect traffic signs in highly realistic real-world scenarios, the diversity and the kind of complexity in the image makes doing that well difficult consistently. And so if you build a federated system that can have a sort of an open world approach to how it trains on the data and can adapt to different situations, you're likely to be able to build much better models. And so I'm really interested to see how he's built this and what the kind of new insights are. And yeah, so welcome. Thank you much for joining us. And I'm really interested to see the work that you've done.
Thank you. Thank you for having me here. It's an honor to be here. So let me share my screen to be able to show you my presentation. So do you have my screen? Is it okay?
Yep, looks perfect.
Thank you. Thank you. As you told, our project is about a decentralized federated learning for um, traffic sign detection in CAVs, which is a stand for connected and automated vehicles. And we experimented this problem in a real world implementation. For short intro, I'm Mehdi Haji, and I'm a final year student, undergraduate student at UT, majoring CS, and I'm a research assistant at University of Michigan under supervision of Professor Wang, which I'm working on the reliability of distributed systems. And that's all that I have. I want to present my presentation in 4 steps. First of all, I want to explain the situation that we are nowadays. So now the cabs, which are automated vehicle in our daily lives, produce enormous amount of data, which generates, for example, sensor data on the order of terabytes per vehicle per day. And for example, to support navigation or other safety function, for example. And also, these are the real application of machine learning in our daily lives. For example, you can apply road damage detection or pothole detection, or even, for example, general object detection, human detection, obstacle detection, and so on. And also, the traditional approach was that we trained this model on a centralized server. For example, first of all, we aggregate all the data from all our vehicles, all of our clients, and then we train our model on a server, um, and then share the trained model with the other clients. But using federated learning, we have applied a new approach. For example, you can see what if we share these images to our, for example, vehicle manufacturer. It's obvious that where we are, or even if they have, for example, timestamp, they can know whenever the place that we are. So it's a really issue. It's a really big issue to us, and we need to solve it. This is when the federated learning approach helps us, which you can train your model locally, and then you can only pass the um, model parameters to the server, not the data, not the pure data. And by using this, um, save your privacy and didn't share any personal information or personal images. So this is the approach of federated learning, and the key benefits of this approach are, for example, as I told you, privacy preserving and also efficient communication, since you don't share your images and only share some pure integers and as a model and parameters. And also it's personalized by the shared model. So the next stage that I want to explain is our complication, which are our real world challenges in a federated learning system for calves. For example, first of all, in first experiment, I want to explain that what is the best configuration for this federated system to address all of our issues. For example, we have to illustrate and examine what's the best configuration, such as number of the server rounds or number of clients or local epochs on each client. And then I will address the second and third issue later on my presentation. So first of all, to solve this first problem, to solve the first problem, uh, we can use a RCNA, regional based convolution neural network, which first of all it will draw a boundary box around each sign and then detect the class of the traffic sign, which on which you can see what is the sign of what is the traffic sign exactly and where it is exactly, and it will help to the connected vehicle or connected and automated vehicle. So another one thing that I want to go through is that what is the best configuration. We examine it um, for as an experiment on Flower framework, and we implemented a fully FL system to implement this model. It was named Argos. Argos is a myth god with 100 eyes, with 100 eyes, which watching the whole world always. And we implemented this model and we go through the best configuration, and I will explain best configuration as we experimented. For example, um, in our experiment, we examine task distribution and also a local model training hyperparameter, and also federated aggregation strategy for the server. And so let's go through the results. And the first result that we got, as we expected, um, IID, which stands for independent and identical distribution versus non-IID. The IID was much better, as McMahon, which he is the one of the first researcher who introduced FL. As he explained, IID distribution is most of the time better than non-ID. So this is the result, which showed. Let me share my laser. So this is the IID, which y-axis stand for accuracy, which in on a same round servers, um, the IID gets a better accuracy. And also we examine server rounds, which stand for how many times the server aggregate all local models. As you can see, the more the server round B, the higher accuracy will be achieved. And also another result was we experimented in our experiment. We examined local epochs. For example, on 8 or 10 epochs provide an optimal efficiency and with a diminishing returning beyond that. And also another finding that we had was client participation and server aggregation strategy. The client participation is a really important issue and is a really important factor to us. Full client participation achieve the highest accuracy. So we need to participate all of our clients in our training. And also another factor that is important is server aggregation strategy, which illustrate what algorithm will be used to aggregate local models on a server. So as you can see, we examine different strategy algorithms like fedaverage or fedadam and fedprox, which fedadam provided stable and consistent gains, but the highest accuracy was achieved by fedprox. Um, Another question that I want to answer is that, but aren't this accuracy or even higher accuracies achievable through traditional ML training processes? If so, what is the power of the federated learning in caps? Uh, I want to answer this question by a quote from Andrew Karpathy. He was the director of autopilot vision at Tesla, which he introduced a new term, so-called data engine, which shows you will train a model and deploy it on the calves, and then you will you will address the rare scenarios when it's a struggle or when you want to see a rare scenarios that happen, which is an unexpected issue on the calves. So by collecting these corner cases at a scale and feeding them in back to the dataset, you can address these issues on the calves. So let me go to the second problem in the real world. The second main problem is that computation resources are limited. Automated vehicles are too busy to spend a significant amount of time on training model locally. So it's in a real world, it's not possible to train a model whenever you want. Um, I will explain it by a question. Um, how to use our resources efficiently, or the better question is how to schedule the tasks in our CAV to address the to solve this problem. For example, one solution is adding more resources, which is not the best one, but it's definitely the most expensive one. Um, but another solution is scheduling the task periodically. In a real-time embedded system, there is a programming paradigm which break task to a smaller task to be able to measure the W sets, which stands for worst case execution time. So we want to break this task to smaller task to be able to measure the worst case execution time. And for solving this issue, most of the times, a real-time embedded system are scheduled periodically. So is it a good way to, for example, dedicate a task to train a model periodically? Definitely it's not, because this task schedule offline. So for example, you will dedicate a long duration for training the model on the period on the system period. So it's not recommended to dedicate a long duration, especially for the um, training model, which which is it not definitely a good use for our model, our resources. Another approach that we can address this question is to schedule the training process using an algorithm named um, a rate monotonic scheduling. So it's preemptive, which it will preempt any task with a higher priority. And for example, the shorter period and the more frequent tasks are, the more resources they will give. And so it's important to see their period and their and examine their period. But it's not an easy work to dedicate a period to a training a federated learning system in our calves because we don't exact period of our training model systems. Uh, this is the explanation for rate monotonic scheduling, which interrupt which more important task will interrupt other task with a less frequent with the less frequency. Uh, so also, rate monotonic scheduling is not always feasible. And this is the main issue. There is a theorem named Leo and Leyland. It's an old one, which shows that you need to have a um, summation of utilization, your summation of utilization must be less than this term. And this is not always easy to achieve this utilization. And this is a sufficient condition to be sure that this task will be schedulable. Also, the short answer for the third question is that earliest deadline first scheduling will help us to improve our system. For example, you can imagine that you have some task, for example, human detection or robot detection and training model for a federated learning system. Um, the first two ones are more important, and they have a closer deadline, so they need to be computed sooner instead of um, our training process or our training task. So the first answer is EDF scheduling, but the third challenge in our real world um, is a really hard one, and it will break the um, latest solution, which is for example, imagine we postpone the training process while the vehicle in a garage. However, we have a long itinerary, and we won't reach our final destination before the FL server aggregation deadline. So this is not a good one because the clients are important to us, the number of clients is important to us, so we want to participate all clients in our training process. So the last question is how can we avoid postponing the federated training process because we don't want to lose any of our clients? This I want to mention that this is different from asynchronous federated learning. In asynchronous approach, you try to update a global model independently and without waiting for each other. But this is about scheduling a training process inside a CAV resources. So this is a different problem. Uh, the first solution to solve this problem is that we can schedule a task in two types. For example, we can have a periodic task and aperiodic tasks, and with two different queues. Uh, and schedule them separately. And whenever the resources are free, we can dedicate some resource to our aperiodic tasks, which are our lower priority queue. For example, we can put training process in this queue, and for example, road detection, object detection, or obstacle detection in a periodic task queue. So this is higher. This is a high priority queue. Um, a better solution for solving this problem is a RM, rate monolithic pooling server scheduling, which shows a server, which dedicate a server um, to a periodic which dedicate a server in our scheduling. The server is a periodic task defined by a period and a computation time, or we can call it capacity, as you can see here. For example, we have two periodic tasks, and we will come. They have their own computation time. This computation time is examined by worst case scenarios. So uh, we can dedicate some resources to these two periodic tasks. And whenever we have a periodic request, for example, our training process, we can um, we can behave and to this process as a periodic task by dedicating the server capacity to this task, to this computation. For example, the polling server work on this way. Um, in every period, it become active and serves pending aperiodic task, aperiodic request up to its capacity. And if there is no exist, if there is no request exists, if no request exists, it's suspend until the next period. For example, in here, this is the arrival time for a periodic task. Before that, we have dedicated a capacity to our server, but there is no aperiodic task. So it suspends until the next period. And on the next period, the aperiodic task will use the capacity of the server to, for example, train our FL system, which is a periodic task. So this was our experiment. We're currently working on our scheduling system to solve this issue. But in our study, we proved that the class-specified federated learning works, and also it's efficient for enough training grounds, and when you use method that handle different type of data. And the next step is to focus on the scheduling for the FL training process, and we are working on that. Other collaborators of this project were Ali Reza Hosseini, Amir Ali Shahriari, and Sohail Hajian. Our tutor was Professor Mudarisi. I want to thank them. And also a special thank to Mohammad Nasri from Flower Lab, and you, Professor, and other Flower Framework team, which enable us to do this experiment.
Great. Thank you so much. You're very kind at the end there. We really appreciate the shout outs. This is great work. Um, I want to ask before we get to any questions, I might have missed it, but you hinted that you were doing some deployments with the system. Um, could you describe a bit more about that? Is this going to be like used for a particular application, or is it a deployment to get access to more realistic data?
In our experiment, we use simulation approach,
Mm.
which on the Flower frameworks. Uh, on your framework, you are able to simulate the process. For example, you can simulate a client and server that are written, for example, in Python. Um, we are deploying on a real cab, on a real vehicles. Um, by Dockerizing the, for example, client codes, and and deploying the server codes on a real server to see more real world challenges, you know.
I see. So this would be driving around in the Michigan area? Is that I should?
Uh, yeah, probably. Why not?
Okay, great, perfect. Let me look at the questions that may have come up again. If you happen to be on the webinar, it's quite easy for me to get your question online. Otherwise, Slack and the other channels is fine. Let me take a look here. Oh, I see. Okay. If someone's asking about applications, they were interested if this method would work for audio, and they mentioned like similar efforts to capture bird sounds. If
Mhm.
you could do a similar thing in that context.
The real challenge on this system is to labeling them. Um,
Mm,
it's not easy to label the data which you have collected. It's a real world problem.
right. Like clicking labels from the edge, and so you're saying that would be a limitation to kind of
Yeah.
shifting for that type of application. Yeah, okay, makes sense. Great.
Mm.
I have another question here. It's quite a simple one, I guess. It's just asking, can this run on a Raspberry Pi? I think some people in the community are wondering about, doing other deployments on their hardware of choice.
Ah. We used mobile network, and
Yeah,
this is not a heavy network, neural
no,
network. But it's not easy to use on the Raspberry Pis. Uh, uh, they need resource. They need a powerful resources, but you can examine you can simulate this on cheaper um, systems, but they are really too slow. For example, in our experiment, we had two, I think, I'm not sure about the name of the GPUs. I think um, P 200, I think. If I'm wrong, you can correct me. We used two GPUs to simulate this process, and each experiment lasts for a couple of days. It was not easy to solve. We would like to examine the real world problem. So, for example, we used a couple of gigabytes for each client to simulate their real situations.
I see. So you're saying, well, 'cause so you're saying that you're using mobile net, and so it makes it quite feasible. Um, but there would be challenges
Yeah,
with
there
those
will be
too.
the challenges. Yeah, exactly. You need to allocate some GPUs to them, especially to train a model in a heavy data, you know. It's not easy.
Oh, I see. So you're not you're not doing local updates on a mobile net architecture on the Pi. You're
Mhm.
doing
Yeah.
no. I see. Okay, that's interesting. I guess we'll make this the last question. The person in the webinar is asking, what was a surprising result from your experiments? Things that something that I guess it's a common question. I guess they want to know, when you're looking over your results, what kind of stood out to you as being unexpected?
Unexpected or expected?
Unexpected. So it was a surprise.
Huh. Uh, for example, the huge difference between IID and non-ID um, was an
Mm,
unexpectedly, you know, situation.
I
Um,
see. So you saw a big magnitude
yeah,
difference, and you really didn't expect that, I guess.
For example, in real world, you are not challenged, you are not able to dedicate a driver to label all kind of the signs. For example,
Mm.
it's better to dedicate a person, for example, to label only animal related signs, or another driver to dedicate it to be dedicated to, for example, warning signs. It's not easy to dedicate persons to label these signs. So the non-ID is more practical way in federated learning system, but the huge difference between non-ID and IID is unexpected.
Yeah. No, it certainly is. It presents quite a challenge. It's like yet another dimension to consider when tuning your system, and
Mm.
you can get situations that are quite realistic, but you would never encounter in a centralized case where you have full control.
Mhm.
Yeah, makes sense. Great. Well, we're fast running out of time, and so yeah, thank you so much for the presentation. Thank you for entertaining some of the questions from people in the community.